That would be really funny, wouldn't it? Okay, so they're just tuning in. They didn't hear that, so they don't know what happened. So let me say it again now. All right. So. Funny. All right. So you're going to build a table for distance problems or time problems. Always build it the same way so that you get comfortable building it, and it will always be worked very similarly. And it's very easy to do. So if you draw your table first, then kind of start organizing your story problem and putting the information into the table, it'll make a lot of sense. You'll have to have a space for whatever it is you're talking about. In this particular problem, we're going to be talking about trains. Then you're always going to have the rate, which is the same thing as a speed. You'll have a time of some sort, and then a distance. And the distance formula always is the rate times the time will always equal the distance. So that formula is what we're basically using. Rate times time is equal to distance. So let's fill in this table. I know it's already filled in, but let's pretend it isn't and see what happens. I have train 1, and it has a speed of 60 miles an hour, and train 2 has a speed of 40 miles an hour. Those two sentences immediately help you fill in some of the boxes. I have train 1 and train 2. Those are the things that I'm talking about, and so that's what we'll put in the first column to identify them. They told us about the speed of train 1. It was 60. They told us about the speed of train 2. It was 40. So just reading that sentence, if I had built an empty table, I would have these all filled in already. All right? Then we're going to go to the next sentence. Train 1 travels the same distance in 1.5 hours less than train 2. Okay, we're talking about the time here, 1.5 hours less, we're talking about the amount of time the vehicle or whatever has been moving. I'm never talking about the time on a watch or a clock, okay? So when I'm talking about time, it's always the vehicle's moving time. That's going to come into play later on, so that's why I'm kind of telling you now. So now, if we talk and read about the times, go back to the age perimeter problems. We're looking for the time that we know nothing about because we need a plain letter T, a naked T. So which train do we truly know nothing about their travel time? Train 1 travels in the same. Train 2 we know nothing about. Train 2 gets the naked T. Then you take that information and you put it up to train 1 and alter it to make it fit train 1. We know that train 1 went an hour and a half less. So it would be train 2's time minus an hour and a half because it took less time. Therefore, it's a minus sign. So far, so good? At this point, you have everything built that you need to actually solve this problem. When we do this, we're going to do the formula like it's intended. This times this will equal this. And you can see that's what they did. 60 times this is equal to this. They put parentheses. You've always got to put parentheses when you have more than one term. So you would say 60 times this, and it would look like this. And you would say 40 times this, and it would look like this. Okay? Here's where you have to decide what to do now. If you have two vehicles going the same direction, okay? Move my paper into, okay? Here's number 1, it's going this direction. Here's number 2, going this direction. They're both ending right there. What can you tell me about their distances that they traveled? They're exactly the same, so they should technically be equal to each other. And that is the strategy here. So maybe you probably want to write this down, maybe right here. Distance number 1 will be equal to distance number 2. And that is exactly what we're going to do to those two little weird values in the distance column. We're going to set the top one equal to the bottom one. So let's do that and do the math, okay? So I would have distance number 1 was 60 times t minus 1.5 That's the distance for number 1, and it's going to be absolutely equal to distance number 2, which was a 40t. Do your good math, do your distributive property, and then try to get the t's all together, because that's what we do in algebra. I try to get the letters together. Okay? So 60 times t. I got this one. Good. 60t. 60 times a negative 1.5 should give you a negative 90. Okay. Your goal is to get your variables together. I would probably subtract what? 60t from both sides. Okay. That would leave me with a negative 90 is equal to a negative 20 with a t. Still got to get the t by itself, so I have to divide. So if I change this 9 over 2 into a decimal, I get that t is equal to 4.5, right? Yeah. Okay, now you go back and you look at your table. What is it going to replace? What is that? What am I going to fill in on that table now? So whose time did I actually find?
Train 2.
I found how long train 2 would be traveling. What is the question about, though?
How long does it take this train?
So I actually have to go back and find both answers, don't I? So if this train was 4.5 hours, if I plug it in here, what am I going to get? 3 hours. So did I find exactly what they wanted me to find? Yeah. Was that okay with the table? It's not too bad. Yes, ma'am.
The kind of confusion when you set up the problem. I understand how the distance equals distance.
Right. You understand the distance equaling the distance?
Yeah.
Okay.
Set it.
Okay. Basically, you're going to build this table, and then just from reading the problem, you're going to try to put whatever you can in whatever box it belongs. And as you get better at it, it will become easier. All right? So let's look at this next one and see what happens. Now, this one's different. This is opposite directions. So if I were to have, Caitlin standing at this doorway over here, and Thomas standing in front of my desk where the burgundy thing is, and they were walking towards each other, okay, would you be able to understand that the total distance they covered would be the adding of Caitlin's distance and Thomas's distance together would make the total distance that they walked? Does that make sense? Okay. Opposite direction problems are like that. You're going to have things going in the opposite direction, so I would have something here going this direction and something here going this direction. Their total distance from here to here would be the adding of this piece to this piece, right? So that's the strategy on opposite directions. So let's fill in this table and do that strategy. So it says, Fred is walking towards John's house at 3 miles an hour. So I have Fred and John. That's my first filling in the table. There's Fred, there's John. I'm talking about some people. And Fred was walking towards John's house at 3 miles an hour. So that would be his rate or his speed. Fred was going 3. John is leaving his house at the same time and walks towards Fred's house. So they're kind of going towards each other. They're going on the same path, and Fred is going 2 miles an hour. So Fred went 2 miles an hour. Are you okay with this now, Maria? Okay. Now it says, how long will it be before they meet if the distance between their homes is 4 miles? So if I have from here to here being 4 miles, and I have Fred walking this direction and John walking this direction, their two distances added together should equal the 4 mile total between them, right? We have no idea who's been walking longer. They gave us no information at all about either person's time, did they? So that's why both of the gentlemen here have plain letter T variables. All of their time is unknown. I have no idea. So that's how they have the plain T. Multiplying straight across, 3 times T would create our distance for Fred. 2 times T would create our distance for John. So I know that Fred was a 3T, added to John, who's a 2T, has to total the 4 miles that they said was between the two gentlemen. Right? Let's do the math. What's 3T plus 2T?
5.
Okay. So I have 5T is equal to 4. I have to get the T by itself because I'm trying to find their time. And it appears that their time is 4/5. Yeah, Mom, I'm going to Sally's house. I'll be back in 4/5. I just don't think that's a really good answer. It doesn't make sense, does it? All right. So what was the reference in the time that we were talking about? How fast were they going? Miles per hour. So this is 4/5 of 1 hour, right? So how could I find that in minutes? Because I'm still not going to say, hey, Mom, I'm going to be back in 4/5 of an hour. Look how good you are. Okay, awesome. Nice job. Okay, so this got converted into a 0.8, right? And then if you times that by the 60 minutes in an hour, you will get 48 minutes. Now, I know for a fact I'm still not going to say, hey, Mom, I'm going to Sally's and I'll be back in 48 minutes. Because that's, I don't know, it might be 49 minutes. I would probably be saying, I'll be back in about an hour. Okay? But 4/5 of an hour does not make sense to the normal person. 48 minutes, they at least have an idea what you're talking about. So make sure that your answers make sense to a normal person. Okay? Have you got any questions on that one? Those are my favorite ones of these. Those are my favorite ones, opposite directions. Okay? One more type. And this is when you're going to someplace and turning around and coming right back using the same direction. You got to go deliver something, drop it off, turn around and come back. That type of thing. Okay? So would you agree that if that's the situation, this is called a round trip or a to-from problem. If I was at home and I go to the big store, I go to the store, I pick up my stuff, I come home directly. Would you agree that that situation says the distances are going to be the same? We always assume we're taking the same route, okay? All right, so that's going to be your strategy on this one. The distance there is going to be exactly the same as the distance coming back. So I will set my two distances equal to each other in the end again. So let's see what we've got going on here. A cargo plane flew to the maintenance facility and back. It took 1 hour less time to get there than it did to get back. The average speed on the trip was 220 miles an hour, and on the way back it was 200 miles per hour. How many hours did it take to make the trip? All right, so let's set up. We're going to someplace and then back home from someplace. So some people go to and from. You can do whatever you want, there and back, whatever you need to make it make sense to you here, okay? Now let's see if we can figure out what the speed or the rate was. On the way there, what did it say? 220. So that's why there's a 220 here. The average speed on the way back was 200, so those two got filled in pretty quick. The time. It says it took 1 hour less time to get there. So we know something about getting there, don't we? Mm-hmm. So which one gets the naked variable? The coming back from. That's the one we don't know. So we start with the plain one, and then if it took an hour less time, we subtract 1 because it took an hour less. We multiply straight across. Once again, we have two things, we have to put them in parentheses. So what is this actually going to be? 220 t minus 1. Very good. And on this one, multiplying across, 200 with just a t. And we already established that my two distances are equal to each other. So we need to do that. This distance is equal to this distance, and work it out. So 220 times the t minus 1 going there is the same as coming back. Do your distributive property. Try to get your variables together. Probably subtract 220 from both sides, do you feel? Mm-hmm. Okay. So I get a negative 220 is equal to a negative 20t. Still working on getting that t by itself. Got to divide, right? So if I divide both sides by the negative 20, it should be a positive answer. So I get that t is equal to 11. All right. Are we done?
Nope. No. You have to find time for a 2.
Oh, okay. Okay, so if this one is 11, 11 take away 1 would be a 10. So did I find the answer?
Yep.
No, I didn't. Read the question one more time.
Hours.
You found both parts, but what do you need to do to those parts? What's the question? What's the question asking you? How many hours did the trip take?
Oh, so you have to add up. 21 hours.
So you need to be careful when you're doing these and make sure you're answering that question. You did good math, but you didn't answer the question. So the total answer would be, it took 21 hours for the trip. Okay?
That's a long time just to
It is. Huh?
That was for a different problem. A cargo problem.
Are you okay with this idea, though? Just make sure you're reading that last question every single time before you say it's your final answer. Okay? Okay. I'm going to pass out a worksheet. We're going to kind of label the problems to let you know whether it's example 4, 5, or 6, so you can go back and look at the tables to try to get them kind of straightened up. All right? So I'm going to put these people on hold here temporarily. Pause. There they are. Did I pause them? I don't think so. Did I? Nope, not yet. Okay, there we go.
Nope.
Did I work? Okay, yay. All right, so I've unpaused these people, so welcome back. And let's talk about our worksheet. If we look at problem number 1 on this worksheet, we need to figure out which table it kind of matches. What type of problem is it? Same direction, opposite direction, or round trip?
Same direction.
It's the same direction, so that's example number 4. So maybe put a little number 4 there. Hashtag 4. All right. How about number 2?
It's the opposite.
It's good. It's round trip. Number 6. Hashtag 6.
No, I didn't.
All right. Somebody had their Cheerios this morning. How about number 3? Agreed. Agreed. Example 4. And number 5 and 6. Uh-huh. Because you know how, the length of the rectangle, those are those naked variable ones, right? The distance. So there's some stuff you should know. They just aren't travel problems.
So 5 and 6.
You're doing them. 5 and 6 you know how, but they're the age perimeter problems, right?
Wait,
Yes.
4 and 5, you mean?
4 and 5. I'm sorry, 4 and 5, yeah. Sorry, 4 and 5 are the age perimeter problems. What about number 6?
Opposite direction.
Opposite directions, because it says so right there, so that's example 5. Hashtag 5. Number 7 is a bit tricky.
Wouldn't that be,
It's one direction, one person, actually. It's just dirt. It's just dirt. There's one person, and it's just dirt. So just see if, yeah, number 7.
But her friend.
Yeah, but her friend doesn't, but when you really think about it, it really is just a single dirt problem. So distance is equal to the rate times the time.
okay, so
Okay.
it's just not an example.
Yeah, it's not one of the examples. It's a special problem. Okay? And if you struggle with that one, I'll help you with that a little bit tomorrow. Number 8. When?
Oh, same distance.
Number 8 is example 5.
Opposite direction.
Yeah. Number 8 is example 5. It's an opposite direction. Number 9.
Wait, isn't it the same?
Yes, is example 4. Some people should pay attention to their notes. And what about number 10? Is this example 6? It's a round trip. Numbers 11 to 14 are going to be bonus if you decide to do them. Okay? So you can build tables to make all of these work. Number 7 is really the only one that might give you a little grief. Okay? So that's your assignment. You've got some time in class. Maybe you want to just try to set some up